Yeah, welcome to class again. This time it's not Professor Forney, it's me. So my name is Ralph Carter. You guys have substantial chalk here, there might be. And I'm visiting here from the University of Illinois. So Professor Forney thought I could teach this class here. All right, let's see. Okay. So I understand last Wednesday, you went through all the finite field stuff, meaning, so you know what that would mean, what that would mean, the finite field with p elements, p to the m elements, that whatever q you have here is the power of a prime in order to be a field. So this one has a notation, it's the ring of polynomials. You have seen that too. And so I assume you know everything about finite fields that you will need to know here, at least. Except for one more theorem, which Professor Forney told me he did not cover. And this is the fundamental theorem of algebra. I have to write a little bit smaller with this thing here, right? Otherwise I'll run out. Oh yeah, that's probably better. Better. Mental of algebra, at least that's what it's often called, and really about 60% of all the proofs in algebra eventually boil down to this here. And what it says is polynomial of degree m, right? F of beta equals 0 at most n. Of beta. At least that's one way to formulate it. Let me see. Yeah, so that's fine. That's fine. So what it says is a polynomial of degree m has at most m roots. Right, so you all have seen that probably one way or another, but because of its importance, I want to emphasize it once more. Do we need a proof for this? In true MIT spirit, we do. And the proof would go something like this. You look at problem number 1 in your homework assignment. And from problem number 1, I could prove that here too, but since it's in the homework, I won't. We can write the following, given any beta. Write f of x as f of x is equal to plus alpha, where alpha is in the field. So that's by some sort of long division you get to that. This is what I'm not going to prove. Then f of beta is equal to 0. It's the same as saying that alpha is equal to 0. So if beta is a root of the polynomial, so 0, it follows that f of x has this thing here as factor, as h of x, x minus beta, where, because of the degree properties of polynomials, h of x is m minus 1, And so the rest follows by induction. So basically, then we can prove that this polynomial has at most m minus 1 roots and so on. Then we can descend this route. So the rest follows by induction. In particular, we can say if f of x has m distinct roots beta 1, beta m, then it factors completely into the linear factors like this. So, okay. I just wanted to quickly state it, the fundamental theorem of algebra, since we need it in a proof later on. And I think you didn't go through it. Okay. So last time you learned everything about fields, finite fields, extension fields. So chapter 8 is pretty much what we have to cover now. So what is the whole idea of chapter 8? It's linear codes, MDS codes, and Reed-Solomon codes. Oh, by the way, do you have any questions about this here? Is that in any way? It's pretty straight, right? Okay, so I understand in chapter 6 or so you had already linear codes over the binary field. So let's just define codes over a larger field formally. A linear code C of length n, length is a K, the subspace of Fn. So whatever the field is. So F could be any extension field, could be the binary field. So it really generalizes the definition of code, of what a linear code is. Okay, so it's a subspace. What can we derive from that? Since it's a subspace, it's a group. And when we can derive minimum distance properties. So let's first define it again. Since it's slightly different than the definition for binary codes, between Fn, say Fqn, so I denote vectors with an underscore. I think in the notes it's boldface notation, so translate that online as I go here. The distance between two words, x and y, given as dx, the number of positions that xi is unequal to yi. Yeah?
What's the subscript of that?
That are q. Oh, this is another thing I should warn you about. My handwriting is bound to deteriorate during class. So I usually start out reasonably okay. Towards the end of the class, I tell my students in Illinois to throw little pieces of chalk at me when it gets too bad, and I'm not facing them. So please just say something if it gets too bad. Yeah. So distance is defined as that quickly. So it doesn't really matter what the values are. Here the xi and the yi could assume different values. It's a somewhat coarse measure for the difference between code words or difference between words. Why do you think I say it's coarse? In digital communications in particular. Huh? It's a Good question, right? In the end, we want to map that into a modulation scheme, right? In the end, we want to map our codes that we are deriving here into modulation schemes. In the end, we want to embed them in some Euclidean space. Now, different elements of our alphabet will map to different elements in Euclidean space. So basically, approximating their distance relation in Euclidean space, which we are really interested in with the Hamming distance here, is pretty coarse, but what we can do, so we do that. It's an approximation at least. Okay. Is that clear, Rasad? All right.
Over F2, the Hamming distance was pretty much the same as the Euclidean distance.
Well, it depends on the modulation scheme. It very much depends on the modulation scheme. If you have an 8PS key scheme, right, where you would label the words here with 3-bit symbols, or with a symbol from F8, right, then it's definitely different, right? That's definitely different. So if you do antipodal signaling, then it's directly reflected. Okay, I'm starting to digress already. So just for completeness, minimum distance, minimum Hamming of a code subset FQN as D as a minimum element code of DXY, and they have to be different. That's the same as before. So now I claim that so the minimum distance of a code is also given by the minimum between 0 and x in the code, 0 and x, and this is minimum of the Hamming weight of x unequal to 0 x in the code. So that's all old stuff. I just write it down so we slowly get started here. Is that clear from the group property? Right, why this would be true? So if we just take this, we can add basically x to both x and y, just translating the whole relation to somewhere else. So in particular, we translate it here. Once we have it here, then the distance between 0 and x is just the weight. Okay. So far, so good. What now is next? Generator matrix. This is not really in the notes, but I think it's important. So C, the code here is a subspace, right? It's a linear space. So it has a generator. It has generators, k generators. So let G1 be k generators of the code. So it's a basis of the vector space. Right, this would be a basis of the vector space. Any basis would be fine here. Then C may be defined as all the x in Fqn such that x is sum over, what do I call it? Fi gi, where Fi is in Fq. And the reason I introduce this, we can That's just the definition of a space, right? That's clear. So if you have these generators, define a generator matrix. Oh, it already starts. Let me. Matrix G, which contains as a matrix containing the rows Gi. So the ith row in the generator matrix is just Gi. Then we also can write as x is equal to f times g f element fqk, which is the same statement as this one, so nothing has happened. So basically the reason I did that, I wanted to introduce the term generator matrix, right? Which is sort of important. And one more property of this orthogonal complement of C, of the code. So what does that mean? So the orthogonal complement of the code we could write as Fqn such that sum of xi, yi is equal to 0. The sum is obviously over the field for all y in the code. What's the dimension of this? Of the orthogonal complement? N minus k, clearly because we have ambient space is n-dimensional, we impose k linear constraints on this by the k generators. So the k dimensions of the taken out by the generators drop out. So dimension of the orthogonal complement is n minus k. Is n minus k. So what else do we need to say about this? C is called the dual code for obvious reasons. C is called the dual code. In particular, it's a code, it's a linear space, it's a subspace of Fqn again, it's a code. So it's just as nice a code as C at this point in time at least. At this point in time at least. So it's called the dual code to C. If it is a code, it has a generator matrix. Let H be a generator matrix for C dual. So in particular, we could define C dual now, for example, by the equivalent of this relation here. But because it's a dual code, we now also can define the original code in an equivalent way such that x times H transpose is 0. Right? We could define our original code C either as the image of a matrix G, of a generator matrix G, or as a kernel of a parity check matrix H. So H is a for C. So that's all pretty much straight linear algebra, and I'm sure you have seen that in many different places. Any questions about any of this? Yeah. Yeah.
So in the definition of the dual code, the summation xi ya equal to 0 for all y other than x, right? Is that necessary? Or?
No. It doesn't have to be different from x. If y is in the code, right? If y is in C, then x has to be orthogonal to it. They can be the same vector. In particular, if you have binary vectors, an even weight binary vector is orthogonal to itself. It's a little bit odd, but that's the magic of finite fields. Okay. Good. So these are codes. Now we could stop. We have defined the object. And obviously it exists because we could just write something down and it exists. So once we have defined it, the next question is, what sort of codes do exist? So, and that's what we're going to do next. First question 1. Codes do. What type of codes do exist? So, which codes do you know? You know Reed-Muller codes, you know probably sporadic binary codes that are out there. These are all binary codes. So what type of codes does exist over larger fields? All right, many classes. There exists the equivalent of the Reed-Muller codes. There exist query Reed-Muller codes, and there exist generalized Reed-Muller codes, and. But we are interested in a very special class today, which is MDS codes. It stands for maximum distance separable. For this, it's a strange name. There's no particular reason for MDS, but let's see what we can do there. What type of codes do exist? So we have parameters of codes, or I think you write it with a curly bracket, right? The n, k, and d. So that would mean a code of length n, dimension k, and distance d. And let me add something to it, a q, if I want to emphasize that this is over the query field. Okay, so are all numbers possible here? Right, do we have a 20, 19, 17 code over, I don't know, over F8? Is this possible? What would you think? Huh? No? It's not possible. Huh? It doesn't seem likely. Somehow, what conflicts here? Yeah, what conflicts here is the dimension and the distance, right? If we get a large dimension, in particular, if we would make this 20, what would that mean? It would mean we have to take the entire space. If we take the entire space, then the minimum weight word has 1. So this is possible, right? We know this is possible. If we drop this by 1, it does seem very unlikely that we would get a 17 here, right? But what do we get here? 2. We get a 2 because that's what we can achieve with a single parity check code. Right? The parity check code doesn't have to be restrained to binary, right? Why? Why would it be restrained to binary? Right? You could just, the set of all vectors, let's define the single parity check code, SPC, Q, is a set of all vectors such that sum of the xi is equal to 0. Right. So could we have a word of weight 1 in here? Obviously not, right? If it has a weight 1, how would it add up to 0? This one position would never cancel with any other position. So the minimum weight is 2 here, and we get a distance of 2. So good. What's the next one? It's tempting to say 3, right? 3, but this is very much a question now. Because this is not as easy to come by as a single parity chain code. And that's what we're going to do next. We're going to find bounds on the maximum distance that a code can have altogether. Okay. So let's do the following, which parameters possible. Okay. So let's assume we have a code, an NKD code, and now we want to find a relation, a bound between NK and D. How do we do this? Any ideas? You let a computer run for eternity and find all possible codes? No. We don't do this. We wouldn't get far. Let's assume we have an NKD code. What does that mean? Well, let's write the code words all down in a huge matrix. So each row in this matrix corresponds to one code word. So this has a length n. This is q to the k. Q is whatever the alphabet is of the code in question. And now we say it's an NKD code. What that means, among other things, is, say we delete. We just puncture out d minus 1 positions in this. Right? We puncture out d minus 1 positions of all code words, and we look at the code that remains. You guys don't have colored chalk here, huh? All right. We look at the code that remains. That means we look at this part of the matrix. Is that clear what I'm doing here? So if the code indeed had distance d, right, can there be any two rows equal in this part? Remember, we punctured out d minus 1. Right. Can there be any rows in this part that are equal? No, right? Couldn't be. They all have to be different. What does that mean? They all have to be different, but how many different tuples can we have in this part? Well, we have at most q to the n minus d minus 1. That's the length here. This n minus d minus 1. Different tuples. Different n. Different tuples. Right, so how can we patch that together into a relation on the parameters? Right. It basically says q. This is q to the k. Q to the k is upper bounded by this, right? It's upper bounded by this. And then we take the logarithm on here, and we get this relation. That's the first incarnation of the tension that we get on code construction, on codes, right? A bound on this at least. If we choose d large, the distance large, then k has to drop. Right? If you choose k large, the distance cannot be very large. So this is where we for the first time see this tension, and it's also written, oh sorry that I run around like this here. N has to be at least k plus d minus 1. So here you see this 2018-3, right? It would just satisfy this. It would just satisfy this. So do we know it exists? No. No. Why would it? I mean, so far, we only have looked at this here. And so if it would exist, it would have to satisfy that. But there's no reason to assume it exists. At the moment, at least. OK. This is called the singleton bound. Any code over any field phi n this relationship on the parameters. Good. Any code satisfying and bound with equality is called MDS. So we have an MDS code if and only if it satisfies the singleton bound with equality. That's the definition of MDS codes. And now it makes maybe a little bit more sense to talk about maximum distance separable codes. Well, in a sense, they have the maximum distance among all codes. Right, all codes with a given n and k, if the MDS, they have the maximum distance. Okay. Let's think a little bit about this here.
One thing. There is no dependence on Q in this relation.
Yeah, there's a very strong dependence on Q. The bound, not. Right? The bound has no dependence on Q. If the guys exist or not, that's very much dependent on Q. And we'll get to that.
Because if Q is large, we have more options to put in.
Absolutely, absolutely. For binary, here's a very simple argument to show that there are no binary MDS codes except for the parity check codes and the repetition code and the trivial code. So say we have a binary code, a binary NKD code with the generator matrix. So what could the generator matrix be? There will be an identity part. So, and then there will be the rest of the generator matrix. And how could we possibly fill that in order to make it MDS? Right? Because of this is n, this is k, and we see in order to make it MDS, every single row have to have all entries equal to 1. Right? Because if not all entries are equal to 1 here, then we immediately have exhibited a code word with a weight less than n minus k plus 1. Right? So okay, we know the first row has to have all 1s. because now the weight of this row is exactly on the MDS board. What about the next one? Well, the next one, same thing. All entries have to be 1. But now we see the problem, right? Now we add those two guys. It should again be a code word, and we have a weight 2 code word. So this is in a nutshell a proof that there are no binary MDS codes except the trivial ones. So the trivial ones are n and 1, and n minus 1, 2, and n, 1, n. These are the trivial ones, right? The space itself, the single parity check code, and the repetition code. These are the only binary MDS codes. And the argument is roughly there. Okay, where was I? Yeah, let's think about this a little bit more. And we are getting to exactly your question about the field size. This here has to hold, this argument has to hold regardless which d minus 1 positions we puncture out. Right? This argument has always to hold. Which means, think about it, it's an enormously strong combinatorial condition on the code. So you have a code, that means you have a code, you write it in a matrix like this, all the code words. You puncture out an arbitrary collection of d minus 1 positions, and the rest, the remaining positions, have to make up the entire space here, the entire space fqn minus to the right exponent. Right, this is a very, think about it, I mean, just writing down this, that's an enormously strong combinatorial condition. So, and that will actually lead to the codes existing only for a very, very special, or for a subset of field sizes. In particular, like you said, we have to have enough freedom in the field size to fill up those, to fill up this matrix to satisfy this. Okay. Before we get to that, before I say a word about the field size, let me formalize what I just said here, namely that all the other positions have to be exactly the q to the n minus d minus 1 different tuples. In a definition, let be a code with q to the k code words over alphabet fq. Let subset of the positions, subset of the positions in C I is called an information set if C constraint to I runs exactly through all q to the k, through all the q to the k fqk. Right, so what it means is you have a code, right? You have a code and you have a subset of positions, maybe this one, this one, this one, this one. This is a subset of positions if the code words, so if the matrix that remains after you take out the punctured columns runs through all the q to the k elements of fqk, then this is an information set.
Constraint to I or constraint to I complement?
Constraint to I, because I has size k. Right. I is it's just about enough to describe every code word. If the restraint of C to the set would indeed give a unique vector for each code word. The reason to call it, so this is the definition of information set. The reason to call it an information set, it's pretty straight, right? Why is it called an information set? Because it's enough, right? Because it's enough. If you know exactly the value of a code word in these positions, then it is enough to recover the entire code word. Right, some genie gives you a code word which was corrupted by noise or something, but tells you these k positions are okay. That's enough. That's all you need. That's an information set. You can recover the information from there. Actually, it is an application that pops up sometimes. That somehow you get side information about some positions in a code word indeed being correct and others not. And others you don't know about. So that's an information set. With respect to our MDS code. So with respect to our MDS code, a corollary of the singleton bound corollary is any k positions in an MDS code are an information set. Information set. All right, so any k positions are an information set. It's a really strong property, really strong combinatorial property. Okay. So far, so good. This is so strong, this property, that we can say something about these codes even without even knowing if they exist. So far we have talked about these codes as if we knew they existed. Well, it's not entirely trivial since we know those guys here exist. So it's not entirely empty. We're not out in cuckoo space here. But do any other ones exist except for those? That's the question now. Right. We don't know that yet. We will show in a little while that they do, but we don't know that yet. But the interesting part is we can derive properties of those codes without even knowing if they exist. Right, and how do we do that? For example, we want to derive the following property. How many words of weight D exists in a linear MDS code? One could ask that, right? If they exist, they're nice. And if they exist, we also want to know how many words do exist at minimum distance. Because that translates, again, directly into union-bound arguments later on probability of error. So that's a good question. How many words of weight D exists in a MDS code? Let's call this ND. And we want to know how many. So I let you think about this here for a sec while I erase the board. And then somebody will tell me the answer. So how can we think about this? And Let's try to do a similar argument as this one. Let's look at a single word, and let's assume the D positions. We ask the questions, does there exist a code word within the first D positions? It is equivalent to the question, does there exist a code word that covers exactly all D positions? Or yeah, any set of D positions. Right.
And zero everywhere else.
And zero everywhere else. Why is that nice? If you could prove that there exists a word for all D positions, because then we pretty much know what happens. Then we know that, well, if this is true, then there are n choose D ways to choose those D positions. Right? And then within those D positions, and it's a linear code, we can multiply with a q minus 1 non-zero field element. Right? So if we can choose our D positions arbitrarily, then this is a number of words at distance D. So let's look at a word, and let's, without loss of generality, assume it's the first D positions. Right? So the first D positions. So in particular, these would be the first D minus 1 positions, right? Which would mean that this has length k. So if we have an MDS code, this is an information set. Right? So if this is an information set, then we can fill up this thing here with just about anything we want. Right? So we choose this information set to be equal to 1. This is how we choose this information set. And by the property of MDS code, we are guaranteed that there exists a code word which is this part in the information set. Yeah? But we also are guaranteed it's a weight D word. Right? The minimum distance is D. That means all these entries here, they must all be non-zero. In this part. Otherwise it wouldn't have weight D. Okay? And there we have it. That's all we needed to show, right? Because now we have shown that there exists a word of weight D in the first D positions. Right? Is that clear? Right. Not clear? All right. Let's All right. Let's try again. I will say the same words. Maybe it becomes clearer by that. Let's look at a code word. This is a generic code word at first, and we want to answer the question, does there exist a code word within which has support only in the first D positions? Right. So does there exist a code word which is non-zero here up to D and which is 0 everywhere else? Right. That's a question we want to answer. Okay. And here's what we do. We look at this word and say, you know what, let's look at the last k positions, which have an overlap of 1 with this word here because it's an MDS property. So we have this relation between n, k, and d. And since any k positions in a word are an information set, right, so we can choose whatever we want in this part, and this is what we choose. Right. By the property of MDS codes, this corollary, we are guaranteed there exists the code word, which in the second half of the code word looks like this. And in the first half, it looks different. It has something else here. And I say, well, it cannot have any zeros in here, because then it would have weight less than D. So it has non-zeros here. So indeed, we've shown the existence of a code word which has non-zeros in the first d positions. Very simple, right? And that was without loss of generality. You could make the same argument for any d positions. What have we shown? We have shown that indeed we can choose any d positions in the code support a minimum weight code word of weight d. This is how many ways we can choose this. Then we have to multiply it with q minus 1, all non-zero field elements. The reason is we might have chosen this, so we might have chosen omega or omega square here, or just the multiples, the scalar multiples of it. Right. Okay. Interesting, right? This property that any k positions are an information set is really strong enough to prove actually it's strong enough to prove the entire weight distribution of an MDS code. Yeah?
Shouldn't we multiply q minus 1 4 ways to d?
No. Why? No. So then you would get too much. Right? If you write q minus 1 to the d, then you won't want to multiply each position with a different value, right? That would imply that there is more than one code word in the first d positions. More than one code word, so that they are not scalar multiples of each other. If that would be true, then you could find a linear combination which is still 0 in this part, but has an additional 0 here somewhere. But if that is true, then we don't have enough distance anymore. Then it's not an NDS code. Right. All right. So it's indeed q minus 1. It's within each d positions we have one-dimensional space. It's just one code, one dimension. Yeah.
It also suggests that the MDS codes have largest number of minimum weight code words.
Yeah, definitely. Right. Any other code must have less or would have less. Right. But every other code would have to have smaller minimum distance. Right. So, okay. Yeah?
I'm at wrong path. Suppose we let the last k minus 1 position 0, and the one before that an element of the field. And you say that we can do it for any element of the field.
Sure.
Since it's a linear code, some of those n of those code words should be in the linear code, right?
Sure.
So, and because it's a field, also we are guaranteed that there exists an inverse.
Absolutely.
So if we add those two code words, which have all 0 in last k minus 1 and have inverses at the one before, we get a code word which has a minimum weight which is less than the one we have here.
Good question. There is a trick out, right? There's a way out of this. I mean, it's great argument, but there's a trick out.
Can be an upper bound.
No, there's a trick. There's a way out here. That namely, so let's put it like this, right? Here we put in a 1, just for simplicity. Let's assume all the other positions are also 1, right? And then you say there should be another code word which has here an omega, right? I say, you know what? What's going to happen? All the other positions are going to be omega 2. There's no way to combine these two guys to get an additional 0 unless you get all zeros. Unless you get the 0 word. That's what I said. It's a one-dimensional space in these positions. Well, it's a subcode. Okay.
This also tells us how the minimum distance code words look, minimum weight code words look like.
Yeah, it tells you that if you write down the minimum weight code words in a q minus 1 times d matrix, right, you have a Latin square, basically. That's what it tells you. There's in no position, if you have anywhere in here an element alpha an element omega, the same omega pops up nowhere else. Right. There's ramifications of MDS codes in combinatorics left and right, so this would be a Latin square. Yeah, you can learn a lot about MDS codes if you think a little bit about that, and about combinatorics altogether. Okay, where was I? So we know that's one. And actually, in the homework, you're going to do ND plus 1. Right. So the next one. But once you do ND plus 1, do all of them. Right? In a sense, it's just inclusion, exclusion from then on. The first one is sort of the toughest one. The rest is inclusion, exclusion. And just for the heck of it, when you go home and do the homework, write them all out. It's a pretty looking formula in the end. Okay. So far, so good. So we have still talked about MDS codes without knowing if they exist. Right? Except for the trivial ones here. So, and the existence of MDS codes is actually not known for which parameters they exist. So, here's why I give you a research problem. The research problem is problem which is the main conjecture on MDS codes. And it's always sort of tricky. When a research problem has a name, then that signifies danger. Right? Then it means that it's not trivial. The question is, for which KD and Q, for which sets of parameters N, K, D, Q do MDS codes exist? And the conjecture is that, so let N, K, Q, because the MDS code, we can actually get rid of the D here, be the longest length of an MDS code. The longest length of an MDS code, dimension K over an alphabet of size Q. Conjecture is that N KD is less than Q plus 1 for K at least 2 and less, I always have to look that up, less than equal to Q. And K plus 1 for K greater than Q. We'll talk about it in a second, except that N, what is it, 3 2 to the S. So if the alphabet is a power of 2, alphabet size is an extension field of 2, basically. Q plus 2 and Q minus 1, 2 to the S. Q plus 2. Okay, so this is the main conjecture on MDS codes. Basically, it says that the length can essentially be as large as the alphabet size, but not larger. This is Q, yeah? Oh, yeah, NKQ, sorry. Doesn't make sense otherwise. So the length can be in the same order of magnitude as the alphabet size. That gives enough room, enough choices to fill up this matrix with the information set, with the MDS property on the information set. This is the parity check code. This row is just taken out as a trivial code. And then the demon of mathematics conspired that this should also be true. So if you have an extension field of 2 and you want to give it a dimension 3 MDS code, they exist for Q plus 2. Right. There are, of course, reasons for this, but they go pretty deep why they exist for those parameters, and it's just mysterious. And yeah, one can give reasons. On the other hand, it's just all right. They are exceptional enough that they have names. The first one is the hexacode. There's something with a generator matrix. And this goes over F4. So that's an MDS code of length 6. So this is a and 6, 3, 4 MDS code over alphabet size 4. That's the first one, but they in that sequence here. Anyway. Otherwise, we have this conjecture. If you solve this, you're going to be rich and famous. You're going to live in Hollywood, and or maybe not. But you're going to be probably not rich. And you're going to be famous about the couple of hundred people who know about this MDS conjecture. But very smart people have been looking for this for a long, long time. Okay. All right, 20 minutes left. So it's better we define, we make sure those codes exist. Or do you have any question about this MDS conjecture? Okay. Last 20 minutes, let's at least make sure those things exist. Read Solomon codes. So read Solomon codes cover this case. They are examples of codes which satisfy this equality. Okay, so how do we define read Solomon codes? Let's just, in a true mathematician spirit, write down, consider the following. Consider the following code. See? Beta 0. Beta Q minus 1. The beta I are the distinct field elements. The distinct elements in a finite field. F is a polynomial. F is a polynomial, and the degree is less than k. Okay, good. So we have defined the code. So what that means is we start from polynomials. The set of all polynomials of degree at most k, right? So what do we know about that set? It's a vector space, right? The set of all polynomials of degree at most k, we can add them, we get a polynomial of degree at most k. We can multiply them with a scalar, we get a polynomial with degree at most k. It's a vector space. So we take this vector space and evaluate for any element in that vector space, this element in all non-zero elements of the field. Right. In all non-zero elements of the field, and we get a code. We get a set of vectors. So we get a set of vectors in that. So, yeah, I took all elements. Why not? Why not all elements? Strictly speaking, I should have taken one more in order to get the one here. We can talk about that in a sec, what this one more element would be. So it's a code. First of all, it's a code, right? We all see it's a code. And once we see it's a code, we ask what are the parameters. The parameters so length. Well, length is the easy one. It's Q. What is dimension? Dimension of C. What's the dimension? It's a little bit tricky, the question. In Illinois, we had to take a class on teaching, right? To how to become an effective teacher. And one of the things they told us is that if you ask a question, you have to wait for 12 seconds until you get an answer. So what's the dimension? There you go. This mapping, right? This mapping from a vector space to a vector space, right? This mapping, also called the evaluation map, is a linear map, right? It's a linear map, meaning that, well, let's start differently. Let's start differently. Do any two polynomials map to the same code word? Now that you know, that you can answer. Right? Are there any two polynomials? So, are there f of x, g of x, such that f of beta 0, I'll make it an I, so that they coincide in all positions? No, then they would be the same, right? And the reason is because if there would be something like that, then you can just look at h is f of x minus g of x, which is just another polynomial of degree k. And this would have to vanish in all positions, right? If k is less than q, it could not possibly vanish in all positions because then the polynomial of degree k would vanish in more than k positions. Fundamental theorem of algebra, the very beginning. So the dimension of C is indeed k, the same as the dimension of this vector space, right? The dimension of the vector space of polynomials up to degree k minus 1. And the distance, if k is less than q, the distance is equal to q. Distance what is it? Same argument, roughly the same argument. Now think, it's a linear code. So if it's a linear code, the minimum distance of the code is the same as the minimum weight of a non-zero word. What's the minimum weight of a non-zero word? These are polynomials of degree k minus 1. What's the minimum weight of a non-zero word? Well, we start out with the weight 1, and whenever the polynomial evaluates to 0, one of the weights drops out. Right? So I claim the minimum distance is the minimum weight weight of a non-zero word, and this is n minus, well, if any of these polynomials vanishes in all, it vanishes in at most k minus 1 positions. Right? At most k minus 1 of these vectors here, of these entries is equal to 0. So it drops by at most k minus 1. Right? It drops by at most k minus 1. And there we have it. There we have it. There we have, oh, this is, yeah. There we have it. There we have that the minimum distance of the code satisfies this equation. Yeah. Yes, what?
The dimension?
The dimension. So it's the same argument roughly. So I say the dimension, so that is say the size of the code is q to the k. Right? When is the size of the code q to the k? If no two elements in the space evaluate to the same code word. Right? If two of them would evaluate to the same code word, then we would less size than the vector space had. Right? But if two of them evaluate to the same code word, that means this is true for all positions, then we could define a polynomial h of degree k minus 1, which disappears in more than k minus 1 positions, namely in all positions. Yeah. Cannot be, hence the size of the code is q to the k. Since this is a linear map, dimension is k. Right. Okay. So cool, so we have it, right? We have our MDS codes. They exist. Here they are. They are Reed-Solomon codes. Right? Not all MDS codes are Reed-Solomon codes, but the ones we are interested in, they are. Right, so distance is at least this, but the MDS bound is at most this, so it's equal to this. The MDS bound, so the MDS bound says this is. Right? So we're done. So it's indeed, they lie exactly bang onto this. There are MDS codes, Reed-Solomon codes. So that is good. So we know what they are. So incidentally, where do you think this one more point is that we would evaluate our polynomials in? You heard about projective geometries? It's the so-called, there's one more point, it's infinity. Right? You have, if you look at the numbers, in order to close that up, you want to add infinity to that too. And in order to get this one addition in length, you want to evaluate this also at infinity. You will have opportunity to do that in the homework. I looked at the homework and I was pleased to see this problem there. I hope you will be pleased too. Okay. All right. Any questions about this? Let's see what else I wanted to say. I guess it just gives me a few minutes to talk about a few properties of Reed-Solomon codes. A few properties of Reed-Solomon codes. And what did I want to say there? Nested codes, so an RS code with parameters n, k. The way we defined them was like this. alphabet. Q, it properly contains k minus 1 minus. Right. So this is pretty straight from the definition of RS codes, since the set of polynomials of degree at most k minus 1 contains the set of polynomials of degree at most k minus 2. So there are nested codes. Property 1 is actually, you will see this is important, that there are nested codes for various constructions where Reed-Solomon codes take part in later on. A punctured RS code is again an MDS code. Why is that so? Why is that so? Well, do you see it? Say if we puncture a Reed-Solomon code, that means we just choose to not evaluate our code in this position, in this field element. Well, we just drop that coordinate. Right? Does anything change in the arguments we have made? Well, the length is now 1 less. The dimension, well, the dimension is still the same as long as k is not larger than the length of the code. The distance is still the same as the length. The distance is at least the length minus the number of zeros. So that equation still holds. Well, but that's all we needed. Still MDS code. All right, so there was really it was not important. It was not important if we took all field elements or a subset of the field elements for the MDS property. That has nothing to do with it. In particular, in the end, we often will drop the 0 element. Right? We often will choose not to evaluate these polynomials in the 0 of the field. A punctured Reed-Solomon code is an MDS code. So what else did I want to say about this? What else did I want to say about this? A generator matrix. How would a generator matrix look like? Yeah, how would it look like? Basically, we can come from here, right? We can take the generators of that space. Right? So basically, we say that 1 generate the set of polynomials, the vector space of polynomials with, right, so this is the basis of that vector space. Right. So if we map that basis, then we get a basis of the image of the mapping. Right. And the mapping of that basis would give this. So we evaluate the function 1 in all field elements, gives us 1. We evaluate the function x in all field elements. This gives us the next generator of the Reed-Solomon code. Well, 0 gives 0, 1 gives, let's write it like this. We evaluate it in all field elements. These are all the field elements. The next one And this goes up to beta. Okay, so this would be a generator matrix. Okay, so that's fine. So now, in order to make things a little bit more interesting, do I also stop 5 minutes early since I started 5 minutes late? Okay, then I think that's over. Like it's over. One more thing. I mean, for you guys to think about it until you reach home. Then the rest we do next time. So let beta 0 be equal to 0, beta 1, or beta I equal to omega I minus 1, where omega is primitive in the field. Right. Then we can write a matrix V of omega right, and you see that the first k columns, the first k rows of this matrix would be a generator matrix of a Reed-Solomon code. Of course, it's the same as above. If we now delete the first position, we erase the first position, we puncture the first position out, and we look at the rest of the matrix. The structure of the matrix. Does it remind anybody of anything? It's a DFT, it's a Fourier transform. And that's what we started with next time. Right. So think about why this is a Fourier transform, right? And maybe there's a nice analogy. So we get the distance, a distance bound. The distance is at least something, which means it's not impulsive. It's not a single one somewhere. The vector that we get is not impulsive. Maybe it has something to do with a bandwidth constraint in the frequency domain. That's what you have to think about on the way home, and that's it. Thanks so much.